Alright guys, so this should cover everything else. I'm gonna quickly open my calculator. There it is. So question 1 is an electric current of 1.50 ampere flows in a wire. So I look at the problem. The very first thing I think I should be doing is writing down what the current is, or writing down the things that are given to me. Okay, so 1.50 amperes, don't forget the units, flows in a wire. How many electrons are flowing past any point in the wire per second? Okay, so how many electrons are flowing past any point in the wire per second? So one electron carries charge of minus 1.6 times 10 to the minus 19 coulombs. Okay, that I know, or I should get that information from that should be provided in the exam, or at least you should know that much. So this question tests your understanding of understanding of current, the understanding that current is basically charge per unit time. Okay, so charge per unit time, so that's in English, right? I'm going to write that in mathematics. So current is charge per unit time, and more precisely it's amount of charge transported, delta Q, per unit time. So you can imagine like this, there's a piece of wire right here, and there's some charge is being transported, and you're right here, and you're counting how much charge is passing through per unit time. That's what current is. And in calculus, like delta Q for even small change is dQ over dt, or it's just delta Q over delta t. So we have to calculate how many electrons, right? So at this moment doesn't look like we like how to get to that answer, right? But remember, the amount of charge can always be written into in terms of number of electrons passing times 1e, or I should just write e, the charge on one electron. So the total charge will be number of electrons passing times the charge on one electron. Okay, and delta t, of course, it's given in the problem, per second, right? So for us delta t is 1. So current now will be equal to delta Q, which is n times charge on one electron divided by 1 second. And current is given us in SI to be 1.50 ampere, and that is equal to NE, where N is number of electrons passing. So to get that answer, I divide both sides by E, so I get N equals to 1.50 divided by 1.6 times 10 to the minus 19 coulombs. I mean, the thing is, like, here you might be wondering, should I include minus or not? The thing is, like, we're counting number of electrons, right? So it doesn't really make sense to have that minus in there. But yes, I mean, each electron has a negative charge. But also, I mean, this highlights that the definition of current, like if electrons are moving this way, then the definition is that the way we understand current is the current is in this direction. So current is in the direction of the direction of opposite of where the electrons are going. So that can also be understood as where the positive charge is going, if you want to understand that way. So that's why we don't include negative here, and you just divide these numbers, and it will be 10 to the minus 10 to the 19 on the top times 1.50 divided by 1.6, so it's 0.93, which is same as 9.3 times 10 to the power 18 electrons. Let's see this, if the answer is correct. There you go, 9.3 times 10 to the 18. Question 2. Determine the potential difference between the ends of a wire of resistance 5 ohms if a charge of 720 coulombs passes through it per minute. Okay, so this tests two things. First, the understanding of the definition of current, and second, how to figure out a potential difference across a resistor, which we already know because we know the two rules and the convention that we have used and we have seen recitation in classes. So I'm gonna go ahead and solve this one. So we have determined the potential difference between the ends of the wire of resistance. So there's a wire. Let's say this is the wire. Okay, that's A, that's B. So ideally speaking, when we make circuit diagrams, we think of wires being objects which do not have any resistance. But in real world, everything physical has some kind of resistance. Okay, so wires that you see, all the resistance is negligible, but there is some kind of resistance, right? So this you can imagine a simple wire which has some resistance as being as a, like, this will be same as having a physical resistor like that of 5 ohms. Both of these things are the same in our equation, because it says that this piece of wire, it has resistance 5 ohms, and it says that 720 coulombs, some charge, like a lot of them, but they amount to 720 coulombs per minute. That's what is passing in the wire. So that means the current in SI is charge per unit time, right? And then it has to be in seconds because we are working in SI. So it's going to be time downstairs, and this is charge. So I'm just going to write it like this. So I is equals to 720. So you probably will get confused with this, but this is what I'm trying to do here. I is del Q over del T. Charge is 720 and time is 1 minute. So that means 720 divided by 1 minute. Although this is the right combination for the answer, that what is the current, but to get your answer as amperes, you have to have in the numerator charge in coulombs and in the denominator time in seconds, because that's how SI units work. So that means I equals to 720 coulombs, which is correct, but we need to convert that 1 minute into second, and that is just 60 seconds. This implies that 720 divided by 60 is 12. So I is equals to 12 amperes. So that's the first piece of information we get after solving what is given to us. Now it says determine the potential difference between the ends of the wire. So I'm gonna just copy this picture here because they both mean the same thing, and I'm gonna paste that picture here. For some reason it's also gonna pick up this, which I'm gonna delete. Okay, so we've got 5 ohms, right? So this is same as having a resistor of 5 ohms here, and there's some current and it's given to us. So as we have seen, passing through the term of potential difference between the ends, right? So let's say I'm going to do VB minus VA, that is the potential difference between the ends. And as we have seen, as we have developed this sign convention, not sign convention, but this convention in the recitation, and also it's given in the book. Let's say we're traveling like this, right? So we have already seen that when you travel with the direction of the current, you write potential drop as minus I times R. It's just the way we have defined it. Del VB minus VA. Okay. So if we get our answer to be positive, it doesn't really matter, like that, because we are not specified, right? In the problem, are we supposed to do the furthest point potential minus the nearest point, or what? So it might happen that we'll get our answer to be opposite in sign that is given to us. That is the actual answer. So that is perfectly fine, because it's very ambiguous when it comes to what if it is VB minus VA or VA minus VB. So we should not worry about that. So VB minus VA will be just R minus IR, and then I'm just going to call it delta VBA equals to minus current is 12 amperes and resistance is 5. It should give you minus 60 volts or plus 60 volts, doesn't matter. So let's see, 60 volts, that's your answer. Question 3. I hope this video doesn't get very big, but anyway, So we've got a slab made of copper, has a rectangular shape and dimensions as shown in figure 26.1. What is the resistance of it along the z direction? Okay, so along this direction we have to calculate the resistance. So you know that resistance is equal to resistivity times the length of the resistor divided by the cross-sectional area. Okay, so in our case, because we have to figure, so the thing is like the direction is really important, because direction determines what will be considered as length and what will be considered as area. Okay, so because we are looking at we want to find the resistance in z direction, the area will be this, okay, in blue, that will be the cross-sectional area, and the length will be this length. You see this? It's going to be the length. Okay, so area is in blue and length is given in red, because the direction of the resistance that we want to calculate is z direction. So after you have figured that out, it's pretty easy, because area is equal to 2 centimeters by 8 centimeters, because this is a rectangle, this length is 8 and this is 2, but we need to convert these guys into meters. So 2 centimeters 2 to the minus 2 meters, and 8 centimeters 8 times 10 to the minus 2 meters. So you get your answer in meter squared. It's going to be 16 times 10 to the minus 4 meter squared. Okay, and length is going to be 5 centimeters, because length is this distance, right? This is 5, this is 5 centimeters, so it's 5 times 10 to the minus 2 meters is length. So you just use this formula, R. Okay, and this point we don't know its resistivity, okay, because resistance is resistivity times length over area. We know this, we don't know the resistivity. So I think you should be provided with like a list of at least this information, what is the resistance of a copper. Okay, so I'm just gonna look up in your book. Oh, nice. So in your book it says the resistivity of copper is 1.7 times 10 to the minus 8 ohms meter. So this information should be given to you in order to solve this problem. So don't worry that it's not given here, but this should be given to you in your front page or of your exam or something like that. Okay, so we have this, and then we just use this formula, R equals to 1.7 times 10 to the minus 8 and times L is 5 times 10 to the minus 2, and area is 16 times 10 to the minus 4. Everything is in SI, so we already taken care of that, so we're fine. We're going to get this answer in ohms. So use your calculators. It's going to be 1.7 divided by 16 multiplied by 5, 0.53 times 10 to the minus 8 minus 10 plus 6 minus 6, or 5.3 times 10 to the minus 7 ohms. I hope this is correct. Okay, let's see. Awesome. 5.3, it is alright. 5.2, 5.3 is okay. 10 to the minus 7 ohms. That's how you do this kind of problem. Alright, question 4. I didn't do a very good job of hiding the answer, but anyway. Question 4 is, a certain copper wire has a resistance of 10 ohms. At what point along the line? This is an interesting question. I can totally see something like this. It's a good question, basically. So when an examiner person sets up these kind of questions, the C question like this, they are really into this kind of question, because it's just interesting. So what it says that a certain copper wire has a resistance of 10 ohms. Okay, a certain copper wire. So we have already seen in a previous question that, look, in reality, a piece of wire will have some resistance, right? So if this is a copper wire, piece of wire A to B, is same as having a resistance like this, a resistor like this of 10 ohms. Okay, same as this. So don't get confused when it is when everything is asked and you're just given up like in a question it's given this there's a piece of wire. You can just totally imagine that piece of wire, have replaced that. Imagine that you have replaced that wire with a resistance of equivalent resistance that's given in the problem. Okay, so this wire, piece of wire, is same as this having a resistor, that's a 10 ohms. So question part A is, at what point along the length must the wire be cut so that the resistance of one piece is 5 times the length of the other? Okay, so let's say I'm going to call the length of this wire to be capital L. Okay, let's make this diagram big. All right, exactly what I feared. Oh no. All right, should not be that lazy. This wire is here, A to B. Okay, let's say that its length is capital L. The question is asking you to imagine if you cut this wire into 2 pieces, okay, and then length of one piece is 5 times the other piece. Okay, so I'm just gonna call this length to be L. Okay, and then this length will be L minus small l. Okay, now what it's saying is, let's say L equals to 5 times L minus L. It says cut so that the resistance of one piece, no, it's not exactly saying that. Says that resistance of one piece is 5 times the resistance of the other. So let's imagine that this piece, you see, the piece that has length L, okay, that has resistance R, and the piece that has length L minus small l has resistance R prime. So it says that, look, this one piece has resistance equal to 5 times the other piece. That's what it says. And we need to find this length. At what length, at what point along the length must the wire be cut? And the information we have is the one piece is 5, the resistance of one piece is 5 times the other piece. Okay, let's do it. So we know already the formula, rho R equals to rho length divided by area, right? So this is not the same R, but this is just the formula for resistance. So for us, this resistance R is, for the first piece, is resistivity, because resistivity is given by rho. L is the length and area is, let's say, small a. Okay, but for the other piece that is of length capital L minus small l, the resistance is R prime. Rho is the same because it's the same material, it's the same wire, so it's made up of copper still. It's just one piece of that big wire, right? So it's going to be L minus L divided by A. So I'm going to use this fact in this equation right here. So I'm going to replace R by rho small a and small l, 5 times rho capital L minus small l divided by A. Divide both sides by rho, so we'll get rid of rho. Multiply both sides by A, so we'll get rid of A. What you'll end up with is L equals 5 times L capital L minus small l. This means that if you solve this problem, you'll have 5 capital L equals to 6 small l, or small l equals to 5 over 6 capital L. Okay, so that is your answer. At what point along the length must vary? Because so the resistance of one piece is 5 times the length, the resistance of other. That should be 1 over 6 or 5 over 6 of the total length. So that only then you will have that resistance to be 5 times of the other length. So we're gonna check that answer real quick, and that's what it is. 1 over 6 times length. Okay. And okay, of course, so our answer is 5 over 6 times length. So we are talking about the bigger piece. That's what we got as our answer, and the answer that's given there is of the smaller piece. Again, there was this ambiguity here, but both these answers are completely acceptable. And now for part B, it says what is the resistance of each piece. Now this should be easier, because look, what is the resistance for each piece, right? So resistance of the whole thing is 10 ohms. So when it was uncut, it was 10 ohms, right? So R equals resistivity when it was uncut is capital L, and area A was 10 ohms. So that means that I know if I divide both sides by capital L, it's going to be rho over A equals to 10 over capital L. So I know that rho over A is 10 over capital L. Okay, so let's say I'm trying to figure out the resistance of length small l, this piece. So it's going to be R equals to rho L over A. But we already know that I can write this as rho over A times small l, and rho over A is 10 over capital L. So it's going to be 10 times L over capital L. And from here we know that small l over capital L is 5 over 6. This implies the resistance for this piece is 10 times 5 over 6. And this should be 2, 3, 2, 5, 25 over 3, about 8. And that's what we have here. The same thing you do for the second one, for the piece L minus L. The resistance is going to be 5. We already know this. Okay, so we already know this. This guy is going to be 5 times less. So you just divide this guy with, like, the other piece is 5 times less, right? So see, we already have it in there. So R prime is R over 5. This implies that R prime equals to about whatever we got, 8.3 divided by 5. And you should get this answer, 1.67 ohms. So this might be a little confusing, but go ahead, rewatch this part, but you'll get the answer. But yeah, how many more we've got? Oh my god, 2 more. So I guess this is a good place to end this video, and I'm gonna make another one for other 2 questions.